So now we understand big O, right? So actually, to measure your software performance, we have best case. This is actually called small o, and we have worst case, which is called big O, and we have average case. So we can look at like big O. We look at the upper bound, that's blue line above. Big omega below the n, right? Big theta is exact, and small o is, this is like big theta, right? Exact. I mean, there's a detail on that which we're not going to cover at this level. We only look at worst case. Now, if you look at, if I want you to write a program to find sum, you can do either use the loop, right? Keep adding, which is big of n. Or if you use algorithms, which is better, algebra has Sn equals to n plus 1 times n divided by 2. You get a sum, big of 1. So this is what our goal is. When you write an application, we want the best efficiency. Right? Not just, hey, it's going to give the same result. No. We already see that the structure here. It will not give you the same result if n is bigger. It's going to take forever to, if I want to find the sum of billion numbers, it's going to take billion single cycle. But this one is one single cycle. Just like when you go to Joe's Diamond, you want to take the big street, right? Not going to the winning county road, right? Because too slow. Yeah. And take it and then like that. So that's the point of this whole class, their structure that we learned. Okay, so if you look at another one, let's look at how to measure this. Finding a number in a phone book. So if you do linear search, you use the loop. You write an algorithm to search for the beginning, and if we found, then we return. That's going to be big O, which is the worst case, big of n. Is it a better way? Yes. If you just do a binary search by jump into the middle, but assuming this is a sorted list, right? So while we're not finding it, we found the middle, right? If it's middle name greater than target name, search at the first half. Otherwise, search the second half and check for the middle again. You eventually going to find it in the middle, and this is going to cost log n time. Okay. Now, let's look at you should go to course document and get the big O exercises from there. This one should be in 4th, right? Big O of n4. We look at the common one. N square. And this one. So we have n squared plus 3n times 2n, then n squared going to be 2n cubed, right? Plus 6n squared, so this should be n cubed, right? And divided by 10, which is like constant, right? So how about this one? So if you carefully look at this, count equals to n, and I equals to count, and I greater than n. So that means I and n, they are equals. So that means this is never be true. Then this loop will never get into this statement. So this should be whatever expression has 2. So, and it's actually do some comparison here, 3. So it's about big of 3. which we can say big of 1. Right? So this is 1, 2, and the expression is cell 3. I equals to count 3. And actually, comparison, that's 4 here. Right? We got 4. But like I said, if you see that, we're going to assume it's big of 1. Because those are the common notation that we just covered. Right? So, right, common orders of the magnitude, right, is called bounded time. It's not depending on the size, we call big of 1. Right? So this is considered as it's not depending on the size, so big of 1. Okay? So you should try to practice this because you will see this on your midterm test. And we're going to come back and cover the rest.